past the age of 85, you have an almost 1 in 2 chance of developing Alzheimer's disease. Last year alone, the world spent $118 billion treating Alzheimer's. And one of the reasons that this is such a big issue is because we suck at diagnosing it. Currently, the process is that patients go through an interview process where they ask them questions for months on end about their symptoms of memory depletion. This is like if you went in with a broken arm and they just asked you questions for months about how you were feeling before they said, yeah, it's probably broken, and 20% of the time they got that diagnosis wrong. This method literally doesn't make any sense. We should be looking at the brain when diagnosing neurodegenerative diseases. Now, having said that, it is a very complicated organ. We have 1 billion neurons and 1 trillion synapses. And as you might imagine, the way that these neurons connect to each other and the structure that they form has a big impact on the function of the brain. Connectomics is the field of mapping the brain and understanding how specific structures relate to function. This can be done on a macro, meso, or micro scale. So that just depends on how you define one node, so either a large area of the brain, a group of neurons, or a single neuron. A person's connectome is their individual map of their brain. And if done on a micro scale, this could be as small as defining how every neuron connects to every neuron. Alzheimer's can be defined on any of these scales, which means that connectomics could have a massive impact on how we look at the disease. In Alzheimer's, a buildup of plaques and tangles interferes how synapses connect with each other. And this causes the neurons and synapses to die and eventually neurodegeneration. Now, this impacts the entire structure of the brain, and therefore the function goes with it. By using connectomics and analyzing the structure of the brain, we've seen that the brain is organized in what's called a small world network. These small world networks are the same things that define how flight patterns work, for example. Now, why a small world network is so great is that, for example, if I wanted to go from Toronto to Brazil, I could do so fairly efficiently because there are big airports in the middle. And these big airports are called hub nodes because they connect to tons and tons of other airports, allowing me to get wherever I want fairly efficiently. This is the same way that the brain works. If one neuron wants to communicate with another neuron, they can do so through a hub neuron because that neuron is connected to so many others. And this is why the brain works so efficiently. But imagine if this really big airport, such as New York, were just to close. This would be chaos. Nobody could get anywhere, and this is what happens in neurodegeneration. Neurodegeneration specifically targets the hub neurons, and this has a big impact on how the brain communicates through cell to cell. And so function drops dramatically. Small world network can be computed as a mathematical model. This means that we can start diagnosing Alzheimer's using real data. So to analyze a small world network, you need to know 2 factors, clustering coefficient and characteristic path length. Clustering coefficient is the number of nodes that are connected to the node that you're looking at as well as each other. So how many airports are connected to New York that are also connected to each other? Clustering or path length is the shortest length connecting 2 neurons. Characteristic path length is the average distance between 2 nodes when considering all the nodes that are also connected to each other. So in order to be considered in characteristic path lengths, these triangles need to be forming. So the shortest path length for me to get to Toronto to Brazil is 2. I can take 2 flights from Toronto to Brazil, connect through New York. But the characteristic path lengths, when looking at all the different paths I could take, actually turns out to be 1.45. But so characteristic path length and clustering coefficient should both come out to be about 1 in a small world network, and this is really important. So if we're analyzing a brain with Alzheimer's and we can see specific regions where these values don't come out to be 1, we can see specific neurodegeneration in those regions and analyze Alzheimer's using real data, and this is huge. Now you might be thinking, but Cassia, as far as I know, we don't have a full map of the brain, and you're right, on a meso or micro scale, we don't have a detailed map of the brain. But this could have huge implications for things like diagnosing neurodegenerative disease, so how are we going to get this map of a living brain? And living is key. Well, there are techniques that we can use, such as functional magnetic resonance imaging, which detects the oxygen diffusion throughout the brain. But for something like this, the resolution just isn't good enough. There are new technologies coming out, however, which are detailed imaging technologies that allow us to map the brain. And one of them is two-photon microscopy. How two-photon microscopy works is it uses standard dyes but excites them in the infrared. This allows us to image tissues really deeply, which is ideal for mapping a brain in vivo or in a living organ so that we don't have to cut up the brain. And also it works at fairly high resolution, which is always a perk. Aside from diagnosing neurodegenerative diseases, Connectomics also has some other really, really cool applications. For example, we can start planning and automating neurosurgeries. We can use it for drug simulation so that the computer has a detailed understanding of the effect on the nervous system. And even Google is working with the Los Alamos National Laboratory and their Connectomics project to understand real intelligence to develop their AIs. So if we want to understand the brain, we have to start looking at the structure and function, the connectome, in detail. Currently, neuroscience is being taught with a map of the brain that was drawn in 1909. Connectomics, although it's in its early stages, could have some really big impacts on how we understand neurological function. So this is a really exciting field because it allows us to potentially solve and understand some really big problems. Thank you.